All right, ladies and gentlemen, today we are going to work on the second law for an open system. The second law for an open system, if I told you right now to sit down and write the second law for an open system, I think that many of you would get this answer correct. So let's remember what the second law is for a closed system. Okay, for a closed system, what we have is delta S is equal to the summation of the heat transfer and the temperature at which that heat transfer occurs plus sigma. Okay, now open system. What's happening now with that open system, that control volume analysis? What's happening is that there is heat that is coming into and out of a control volume. There's work coming into and out of a control volume. There is mass coming into and out of a control volume, and so that is the difference. So we have to have mass coming in and out here. The other thing we remember from our closed system to open system change that we had for our first law is that this is no longer going to be delta S. We're going to have a rate going on here. So we're going to say the change in the rate of entropy of the control volume with respect to time, just like we said the change of energy of the control volume with respect to time, is equal to the summation of the heat transfer rate over the temperature at which that heat transfer occurs, plus, and here's where we add the summation of all the mass flow rates in times the entropy in, because the mass is going to bring some entropy with it, and minus the summation of the mass flow rate exiting times the entropy exiting, plus sigma dot. Okay, plus sigma dot. That is all there is to it. Oh, I didn't have my sound up. Well, I have to do Jake again. Jake, you guys missed Jake as much as I did, so Jake has recorded some more sound bits for me. So here we go. Here's our first one.
It's like magic.
Yeah, it's like magic, but it's thermodynamics, which is better than magic. It's just wonderful, wonderful stuff. And actually, that's all I need to lecture about today. That is it. That's the second law. That's all there is left in this chapter, really. We have to talk about it. We have to practice it. But that's the material for the third test. This equation is going to help us with it. So what I want us to do now, just be able to talk about this, is in terms of words. This first part of the equation is the rate of entropy change. If it's steady state, there's no rate of entropy change. It's zero, just like it is with energy. These three terms here are the rates of rates of entropy transfer. Okay, we're going to have entropy transferred by heat coming over some temperature boundary. We're going to have entropy transferred by mass coming in and mass coming out. Those are our three ways that we can transfer entropy in a system. And finally, here is going to be the rate of entropy production. And so we know there's three things we know. If sigma is positive, we know that is a real process. That's a real process. If sigma is negative, we know that is not possible. Sigma cannot be negative. We cannot have no entropy or a negative amount of entropy consumed by a process. And if entropy is zero, what is that?
It's reversible.
That's right, Jake. It's reversible. It's reversible. Wonderful, wonderful stuff. All right. So let's take that and let's now start working on some problems. So let's do problem number 1. We're going to have a magical, mystical device. Okay, a magical, mystical device that looks like this. Is a wonderful drawing of this magical, mystical device, and it's insulated. This device is insulated. Okay, we're going to put steam through this device. So here we go. Steam is coming through this device. And I am going to call this first state up here, I'm going to call this first state star, and the second state I'm going to call squiggly thing. Okay, I'm not calling it 1 or 2 for a reason. I'm not calling it A or B for a reason. I'm calling it star, and I'm calling it squiggly thing. Okay, and here's what we know. There's a shaft up here, some sort of shaft, and it's rotating one way or the other. And we know that here at star, it is a saturated vapor, and the pressure is 100 kilopascals. And we know at squiggly thing, our pressure is equal to 1.0 megapascals, and the temperature is equal to 320 degrees Celsius. Okay, we know that those two states. The question I have for you is, what direction is the steam flowing? Okay, so if you get this problem on a test, you have to say, what is this problem actually asking us? Sure, it's asking you what direction is the steam flowing, but the real question is, in which direction is steam flow possible? Okay, in which direction are we going to have entropy production that's positive or zero? We are going to consider reversible systems as the limit of where things are possible. Okay, and negative is going to be impossible. That's what we're trying to figure out. So to do this, the first thing we're going to have to do is set the state here. And so if we have state star and we have state squiggly thing, we are going to look up the entropy and the enthalpy for both those values, because we might need them. Okay, so here we go. H star is going to be equal to 2675.5 kilojoules per kilogram. And S star is going to be equal to 7.3594 kilojoules per kilogram Kelvin. Okay, now at state squiggly thing, H squiggly thing is going to be equal to 3093.9 kilojoules per kilogram. Okay, S squiggly thing is going to be equal to 7.1962 kilojoules per kilogram Kelvin. Okay, we are going to now use those values to help us figure out the answer to this problem. Okay, so what is the answer? Well, we're going to have to write up it's an open system. Mass, if I make my control volume, and I should do that here, my control volume is going to be this. There is this shaft does go inside the control volume. There's something going on here. I don't know what's exactly in there because it's magical and mystical. But we have to draw our second law for a open system. So we have ds CV dt is equal to the summation of the heat transfer rate and the temperature at which that heat transfer rate occurs at the boundary, plus the summation of the mass flow rates N times the entropy N, minus the summation of the mass flow rates Xt times the entropy Xt, plus sigma dot. Okay? Now, what can we eliminate? What are assumptions that we can make in this problem? It didn't say so, or I didn't tell you so directly, but we're going to assume this is steady state. We're going to assume this is steadily moving on. This process is going. Something is happening. We're not in that transient period of this process. So this is going to go away. We know that there's an insulated system. There's no heat transfer. Okay, we know heat transfer. So this is going to go away. Okay, we're going to have some mass flow rate in. We're going to have some mass flow rate going out. Both of those masses are going to bring with them or take with them some entropy. And we're trying to find this sigma dot because sigma dot is what we want to make sure that this is possible. So we're going to rearrange this equation. Sigma dot is going to be equal to the mass flow rate times S exiting minus S entering. Okay, note what I did. I moved this sigma dot to the other side of the equation. That introduced a negative sign. I absorbed the negative sign, or I took everything times -1, and that flipped the order of these two terms. Okay? I don't have to know the mass flow rate. I don't have to know the mass flow rate because sigma dot over mass flow rate is going to be equal to S exiting minus S entering. That's the same thing. That's the exact same thing because this magnitude is going to probably be reduced, but it's still going to be positive, or still going to be negative, or still going to be zero. dividing by mass flow rate doesn't do anything about telling me if it's possible or impossible. So know that. We can do that anytime. Okay? What do we know here? We know very clearly that for this to be positive, S exiting must be greater than S entering. Okay? The entropy exiting must be greater than the entropy entering. It has to happen for this to be greater than 1 or greater than 0. Okay? And how can that happen? Well, look here. That means that this thing has to flow this direction. We have to go from state squiggly thing to state star. This is the direction that we need to go. Now, I've put this problem on a test before, or we've had homework problems about this before. And students often think, well, it has to go from a saturated vapor to a superheated vapor. No, we just don't know what's happening here with the power. We just don't know what's happening. What's going on? Are we compressing this? Are we putting power in? Are we taking power out? That kind of can change things here. Okay, that can change things here. So the next question is maybe what is the power? What is the power? Okay, we couldn't determine this before. The first law doesn't help us here before because the first law we have to use because that's the law that has the power in it. Okay, we have to use our first law. The change in energy of the control volume with respect to time is equal to Q dot minus W dot plus the summation of my mass flow rates N times my enthalpy N, kinetic energy N plus my potential energy N minus the summation of my mass flow rate exiting times my enthalpy exiting, kinetic energy exiting and potential energy exiting. Okay, we know it's steady state. We know it's insulated. We know that there is no kinetic or potential energy effects. We might have been able just to write this equation very much more simple than I did right here, because you've been comfortable with this. What we're going to get is W dot is equal to mass flow rate times Hn minus H exiting. Okay. And I don't know the mass flow rate, so I'm going to ask you, what is the power, I should change this, what is the power per unit mass in kilojoules per kilogram? That's how I'd ask it on a test, on an exam. So I would divide through here by m dot. W dot over m dot is equal to Hn minus H exiting. Okay? Well, we know which one. We know what's Hn right now, don't we? We found that out. We found which way is H in, and we found which way was H out. So what you are going to have to do is do this. This is going to be the top hat question. Find W dot over M dot with the correct sign. That is going to be your top hat question here. I've basically done the work for you. You have to kind of plug in. But I want you to ask the question when you're done with this. Does that make any sense? I mean, it doesn't make any difference if we know how to just plug numbers in. We have to know, does that make sense? Does the answer make sense? If we get this answer as negative, does that make sense? Do we get this answer as positive? Does that make sense that we go from the state squiggly thing to the state star? If you can answer that question and you can make it make sense, or you can talk to me in my office hours and make sure it makes sense, that's the important part of this. Remember, I say remember here, and I'm going to say, I want you to think and not remember how to do these problems. You have to think. I mean, we're going to go into a world when this is all over that we've not experienced this before. There's lots of things that we can do. We can't just remember how to solve these problems or remember what to do or look at what somebody's done before. We're trying things for the first time in many ways. As engineers, that is our duty. That is our job. And you're in a basement of your parents' house, or you're sitting over in an apartment on campus, or you're in your house late at night in your pajamas giving a lecture to a bunch of people. Okay? What you're trying to do is we're trying to do what we can to improve the situation, and we can't do that without thinking. Okay, so I encourage you, in the basis of what we're doing here, with all this craziness going on, still try to see, does that make sense to me? And if it doesn't, ask me a question. I sit here every day from 10 to 11 waiting for you to ding into my office hours for you to ask me questions. I want to help if I can. Okay, I want to help if I can. All right, enter this top hat question and we'll move on to another example.